You have to take action to learn about a complex system, but the wrong action permanently destroys the environment you are trying to understand. Risk architecture focuses on the precise timing of irreversible decisions. This chart plots a system's cumulative stability over time. While a healthy system grows smoothly, an improperly timed commitment causes that stability integral to drop to zero and stay there. We call this specific failure state the forbidden action, an irreversible move executed before verifying that the system's internal form and external position can carry the load. Applying a move fast and break things philosophy to high-stakes commitments structurally burns the base the system relies on. The principle of sequence functions as a commitment-controlled discipline. It does not dictate how an organization thinks. It acts strictly as a gate for execution. This documentation shows the POS authorization gate. The engine takes pre-selected actions and evaluates their indicators to either mathematically authorize or block execution. We are going to construct this exact GPOS Boolean gate from scratch, variable by variable. To build it, the architecture must resolve a specific design tension: how to enforce a hard binary no within a framework that otherwise relies on probabilistic scoring. Operating high-stakes systems on human intuition exposes the base to fatigue and bias. Safety requires a hardwired mathematical sequencing architecture. This scatterplot defines the phase space of actions. To avoid gating every minor decision, the engine must separate actions based on their irreversibility. The y-axis represents kappa, the degree of irreversibility, accounting for sunk costs. Down in the bottom left quadrant, we find probes and preparations. These low kappa actions are left ungated. Systems require continuous, reversible exploration to build baseline capability. The x-axis measures exposure. Even reversible actions require caps, but as kappa approaches 1, we enter the red zone. These are the hard commitments. High kappa actions trigger the full POS gate, demanding absolute proof of readiness before execution. This mathematical separation makes it harder for operators to disguise a massive, irreversible commitment as a routine exploratory test. When an action hits that red zone, it requires proof across two pillars: internal form fitness and external position leverage. This bell curve shows a readiness measurement. In high-stakes engineering, operating off an optimistic point estimate at the peak invites disaster. The engine reads only from this shaded region, the lower confidence bound. The gate only accepts data from the pessimistic tail. The engine dynamically scales the required readiness threshold, theta, based on the stakes of the action. Higher stakes demand a more conservative bound. These values consolidate into the robust readiness ratio. The engine selects the minimum of the form and position scores divided by their respective thresholds. If the RROB at the lower confidence bound is less than 1, the system lacks the base to survive the commitment, making the action readiness forbidden. A favorable aggregate readiness score can often mask catastrophic single-point failures. This is the flaw of arithmetic averages. A soaring surplus in a non-critical area can mathematically hide a fatal deficit elsewhere. This table details the thresholds for high-consequence phases. Even if an operation clears the overall RROB threshold, it may still contain a hidden critical failure. To prevent this, the engine identifies subset critical indicators that are strictly non-compensable, routing them through the HI veto channel. The engine applies this veto as a multiplier. The readiness check is conjoined with the product of every critical indicator. If a single structural zero occurs, like a failed instrument calibration, HI becomes 0, immediately collapsing the entire gate. Wiring the veto as a multiplier ensures that critical non-compensation is a structural property of the gate, not just an operational goal. Even with a perfect readiness ratio, certain actions remain universally destructive. This table shows the failure conditions for the values firewall. The C firewall operator checks the action for legal violations, dual use concerns, and extreme safety hazards. An action being readiness forbidden can be cured with preparation. An action being values forbidden is categorically barred at every readiness level. The firewall is evaluated first and unconditionally. It cannot be bypassed by high-performance metrics or emergency overrides. The completed GPOS equation now represents a comprehensive filter that sequentially proves safety, readiness, and structural integrity. Deploying this gate requires extreme epistemic humility. Mathematical elegance does not guarantee real-world success. Every threshold, weight, and coefficient discussed possesses exactly zero decision authority until it is calibrated. They carry the research use only tag. Explicitizing a measurement formula makes its assumptions inspectable, but it does not make the claim true. This equation defines the counterfactual accumulation gap. It is the core metric for the POS P1 and P2 falsification tests. The system must causally prove that the gated policy mathematically beats the ungated baseline on external outcomes at an equal resource budget. Without rigorous external empirical calibration, any risk gate is just mathematical theater. The principle of sequence functions as a structural guarantee of survival. Compounding success belongs to systems that methodically build and protect their bases, rather than relying on reckless gambles. True architectural discipline means knowing exactly when to withhold energy, ensuring that when the system finally commits, it acts from a base that cannot be broken.